Hello, I'm Pete Harris from ARM, and welcome to this talk on getting started on mobile and best practices for ARM GPUs. This was originally presented at Vulkanised in Munich. The recording during the live event didn't work, so this is a post-event re-record, and I've taken the liberty of expanding on a few topics and adding a couple of slides that I trimmed for time. So if you were at the event and things sound a little bit different, that's why. This talk's going to break into 4 topics. The first is going to look at mobile essentials. What is a mobile system? What makes it an interesting platform to optimize for? And in particular, what makes it different to PC or console platforms? We're then going to look at the GPU architectures that we choose to build to fit this mobile platform and how that translates into Vulkan best practice. How do you use the API to get the best out of these platforms? I say ARM GPU because that's what I can talk about with some confidence. However, most of this advice is common to all mobile platforms. To wrap up, we're going to look at what's new in the ARM Mali GPUs and the ARM Immortalis GPUs this year. Before we get started, a very brief intro to me. So I've been at ARM since 2004, which is really before smartphones were smart. And I've worked on GPU since 2009, which is really about the time that they started getting into the majority of phones. So I've really been involved with smartphones and mobile graphics since the beginning of the ecosystem. Nearly all of my roles have been related to driver performance and hardware performance and developer outreach. So starting looking at optimizing the device drivers, evolving into designing optimizations that go through into the hardware, and then ultimately about making sure applications are using the API the right way. And the reason for that is it's much easier to change an application and optimize something at that level than try and find 1 or 2% optimizations in the driver. So to get the best bang out of the GPU for the power budget, application optimization nearly always gives the best results. My day job is product owner for the ARM Mobile Studio tools. These are ARM's free of charge Android profiling tools for ARM CPUs and GPUs. I'm also maintainer for the ARM ASTC texture compressor, ASTC Enc, which is an open source project available on our GitHub. Let's start by looking at some mobile essentials. So mobile systems use a system-on-a-chip architecture. So all of the processors in a system are on a single logic die. CPUs, GPUs, display controllers, modems, video encode and decode, camera signal processors, and so on. And then on the logic die, we then stack on top of it separate memory and flash dies. Really, the entire computer in this system is part of a stack of silicon under the ARM logo there. This is very good for manufacturing. It's very easy to build these systems. It does help overall energy efficiency, but it does mean that all of the heat-producing components in our computer are ultimately in a very small area on the device motherboard. And the biggest challenge with high-performance mobile software, especially with games where we're using multiple processors, is getting the heat out of that chip so we can run it fast. Obviously, mobile devices are generally passively cooled. There's no fan here. So we're relying on heat spreaders, heat sinks, increasingly heat pipes to get the heat out of that chip and into the case, so that we don't start hitting thermal throttling problems. For devices this year, we're seeing sustainable budgets of between 3 and 6 watts. It does depend on the device manufacturing, and obviously does depend on the user environment as well. If it's a warm day and you're trying to use the phone outside, then passive cooling won't be as effective. This is a bigger number than you may have seen from my presentations in the past. 2 years ago, I would have been saying 3 to 4 watts. And this is just because of physical manufacturing improvements on behalf of the device manufacturers. They're increasingly using larger heat spreaders and heat pipes to get heat away from that chip. So this is nothing to do with the electronics or the GPU itself. This is purely better physical manufacturing. What makes mobile a really fun optimization target is that you have to think holistically. The power that we're generally constrained by comes from the entire system on a chip, CPU, GPU, display controller, memory bandwidth, and so on. So if you're trying to fit inside a thermal budget, all parts of that system have to be working well together. This does enable a different way of thinking about optimizations compared to, say, a traditional platform like a games console. For a console with a heatsink and a fan, they are designed to run all of the components at max performance all the time. So you can generally break it down into 3 independent optimization problems looking at CPU, GPU, and memory bandwidth. Because we're sharing a thermal budget, then you really have to make the whole package work well together. And even if you're GPU bound, you may find that optimizing your software workload or your memory bandwidth actually helps because it frees up thermal budget that can be assigned to increase the GPU frequency. What's inside this system-on-a-chip die? Most obviously we have some CPUs. This is going to run the application software, the driver stack, the operating system, and if you've been around smartphones, you'll know there are multiple different sizes of CPU inside these designs. They look like a single set of multi-core CPUs to the operating system, so the OS can choose to schedule threads onto any of these cores. But the reason we do this is to try and find an optimal performance to energy efficiency trade-off. So the biggest CPUs in the design have the best single thread performance. They can have the highest clock speeds, the widest instructions per clock issue, and they will give you very good single thread performance, but they do that in a way that sacrifices some energy efficiency to achieve that high performance. The little CPUs are the most efficient way of running software, but they're normally slower. They can't achieve the same single thread performance. However, they are normally more numerous. So if you have a workload that can be multi-threaded, rather than running the big core very fast, you could run 3 or 4 threads on little CPUs more slowly. That may be a more efficient way to run your software. Outside of the CPU, we have the memory system. This links all of the processing elements to the memory that we need, to the DRAM. So ultimately we will end up in a memory controller that links the logic die to the wires that go out to the DRAM die. Increasingly for high-end mobile, there's a system cache that sits between the processors on the die and the memory controller. And the reason for this is that can buffer some of the traffic and reduce the amount of data that ends up in DRAM. Now, compared to a PC, that system cache is quite small. So for mobile this year, 2, 4, 8, 16 megabytes is the kind of size that you might see. The reason we try and do this is because DRAM access is one of the most expensive things that you can do. Generally, for the latest technology, LPDDR5 for mobile, it's around about 80 milliwatts per gigabyte per second for the DRAM, the PHY, and the memory system and the memory controller. So if you're pushing 10 gigabytes per second of traffic, then you're going to spend 800 milliwatts to 1 watt roughly on your memory power. 10 gigabytes per second sounds like a lot, but if you're trying to run content at latest phones support 90 FPS display, then that's only going to give you just over 100 megabytes per frame at 90 FPS. And that's really not very much. You can burn through 100 megabytes very easily, especially if you're not following best practice. There's obviously a GPU, and we'll talk a lot more about GPUs later, so I won't talk about that at all now. That's obviously doing all the rendering that we need. And there's a display processor, which handles getting completed swap chain images out to the display. If you come from a console background or a PC background, you may not think about the display controller. You submit images to your GPU and it's all part of the graphics card. For mobile, the interesting thing is that the GPU and the DPU are often from different vendors. The capability set here is often a little bit variable. But they are processors. They can generally handle some amount of composition. That's layering, scaling, rotation, color space conversion, and so on. However, they are hard real-time processors. They have to hit their scan-out deadlines or you get screen tearing. So if the workload is too complicated, the OS compositor may fall back to the GPU to simplify a complicated composition into a simple composition and then hand that to the DPU a little bit later. That obviously increases your GPU workload and the memory bandwidth. That may be an unexpected load in your system. Can also increase latency because you're introducing extra work that has to happen to get that frame out to the display. So for Vulkan, where you get control over the swap chain, it's very important for your application to render images using the GPU in a form that the DPU can handle without needing that fallback. And I'll talk about that a bit more later. We talk a lot about bandwidth, especially for mobile, because it's so power hungry. One thing I just wanted to highlight was the fact that bandwidth is mattering more over time. So if you look at the silicon process physics over the last 10 years, so how much power does it take to do an ad, for example, then we've seen the curve is roughly something like this. This is a PowerPoint graph, don't take it literally, but the trend is roughly from silicon process alone, cost of doing an ad has improved by 10x in terms of energy cost. This is ignoring IP improvements, the fact we've made better GPUs and so on. This is purely the kind of gate cost that the physics is giving us. Conversely, DRAM has improved, but by a far slower rate. So generally we see DRAM gets better by about 15 to 20% a generation, and we get a new major generation about every 3 years. So if logic is now 10x better than it was 10 years ago, DRAM is maybe 40 to 50% better than it was 10 years ago. What this means is, from the purposes of an application workload, is that you can do a lot more maths per watt versus bytes per watt. So a lot of the best practice we talk about is about trying to reduce the amount of memory traffic that your application is generating. As you can see here, this is becoming more important over time. Memory is taking up proportionally more and more of that power budget. And we are seeing games now where more power is being spent on DRAM than is being spent on the GPU itself with the latest ARM GPUs. On the processing side of things, frequency matters. So here we see a graph of power consumption of a processor with the clock frequency of that processor. And clock frequency is a reasonable proxy for performance for many workloads. And what you'll see here is as frequency increases, you get a disproportionate increase in power consumption. So you're paying more and more power for each increment in frequency that we make. The reason for this is that to make transistors toggle faster to get the higher clock frequency, we have to increase the voltage. And the energy consumption per toggle follows a V-squared relationship. So you have to pay a disproportionate cost as those voltage increases start to add up. If you're a PC gamer, you'll most likely know this from overclocking. Pay an extra voltage penalty and have a bigger fan and a bigger heatsink and get yourself an extra 50, 100, 200 megahertz on your processor. The good news for mobile is that the same effect works in reverse. If we can reduce the workload of the application to a point where we can start dropping the frequency and reducing voltage, we get a V-squared saving working in our favor. So for many workloads, especially for mobile where battery life and thermal is so important, optimizing to achieve an underclock is a technique that definitely pays dividends. So that's mobile platforms. How does that translate into the GPU architectures that we try and run on these devices? This is the traditional immediate mode architecture. Once we got off software transform and lighting, this is what the first fully hardware GPU pipelines would have looked like. And it really is a single pipeline. At the beginning, we read the draw calls from the application and the triangles from the application in draw call order. We do the geometry processing, and as we shade the vertex shader, the outputs of that go into a FIFO that is on chip inside the GPU. The fragment processing stage just pulls triangles out of that FIFO and renders them to the screen. This process gives us coherent geometry processing if the application's done a good job and given us a good index buffer. The data access is local and we get good memory access patterns, and the output stays on chip, so the bandwidth for the vertex shader outputs is very efficient. The downside of this architecture is that we are processing triangles coming out of that FIFO in application specified order, and applications generally do front to back sorting, not spatial sorting. That's very difficult. The triangles could be anywhere on the screen, making the fragment working set very large. If you have to keep color buffers, depth buffers, G buffers on chip, you'd need a huge amount of memory. So that tends to be off-chip memory backed in DRAM, and you get higher traffic on the fragment processing side doing read, modify, write access to frame buffers for ZS testing, blending, and so on. For mobile workloads, we generally have a lot of pixels, and quite often reasonably simple geometry, so we'd really like an architecture that gives us much better spatial coherency on the fragment shading side. And the technique that many mobile GPUs take is tile-based rendering. We take the output frame buffer, we split them into tiles, and we shade individual tiles to completion. What this enables is a tile RAM inside the GPU. Those tiles are small, so we can keep all the color samples, the depth samples, the stencil samples, even multi-sample data inside the GPU, inside tile RAM, for the duration of the fragment processing. This gives us much more efficient fragment processing. We have high coherency in spatial terms, and we have guaranteed by the architecture no read, modify, write access from that tile memory to, say, a frame buffer in RAM until we get to the end of the tile and we have to persist it somewhere. So we get much more efficient pixels. The downside is, to achieve this, we need to know all of the triangles that contribute to a tile before we can start shading it. So we take that nice single pipeline that the immediate mode renderer had and split it into two disjoint stages. A geometry processing stage that runs first. This computes your vertex shading data and, most importantly, which triangles contribute to which tiles. That's big, so that we can't keep on chip. So this is a technique that gives us more coherent fragment processing, but at the cost of more off-chip bandwidth to handle the handover between these two phases of processing. There isn't a right architecture here. These two architectures are simply making different trade-offs about the importance of geometry and pixels, and for the majority of content that we see on mobile, we believe that tile-based rendering gives us the best result. So what are the pros of a tile-based renderer? Because the data stays on chip, we get zero bandwidth ZS testing and zero bandwidth color blending. It's guaranteed that the sample data we need to blend with or test against is inside the GPU. That never ever needs to hit DRAM. We can do zero bandwidth transient attachments. If you have a stencil buffer that only has to live for the duration of a render pass, you never even have to write it back to memory. We simply throw away the tile data at the end of the tile. Similarly, we can do the same thing with multi-sample data. We can accumulate the multi-sample values during the rendering inside tile memory, and at the end of the tile, when we have to write it back to memory, we can inline the resolve to a single sample value that gets written back. This makes multi-sample anti-aliasing a really cost-effective technique for a tile-based renderer when it's prohibitively expensive on a typical desktop GPU. We can do zero storage transient attachments, so Vulkan has the idea of lazily allocated memory, so you don't have to back a buffer with physical pages if it's not written. This can significantly reduce the amount of physical memory that your application needs, especially for things like depth and stencil buffers that you may not need to keep. Within each tile, we can see how triangles layer with very tight spatial locality, and we can use that to enable microarchitectural techniques such as hidden surface removal. These aren't specified in the API, but they're the kind of tricks that most GPU vendors will try and do. Throw away redundant work that doesn't need processing. For Mali, we have a technique that can skip tile writes for unmodified tiles, so we can compare a hash of the color against a hash that's been computed in an earlier frame. This doesn't help too much for 3D content, but for 2D games and user interfaces, this can save significant percentages of the overall frame bandwidth. For advanced users, you can start using tile memory as a means of exchanging data between phases of rendering and avoiding round-tripping things to memory completely. A good example of this would be a deferred lighting algorithm using a geometry buffer. You can have a subpass which creates the G-buffer, stores it in tile memory, and then you immediately run the next phase, the next subpass, which will read that G-buffer, resolve the lighting, and write the lit color back to memory at the end, discarding the G-buffer, never storing it to memory at all. Not all of this comes for free. Tile-based rendering is a choice, and that choice will come with some downsides. The first downside is that we have much stricter API rules for parallelism. By making the rendering pipeline these two disjoint phases, one processing geometry for the tile binning and one processing the fragment shading, we have a coarser structure that requires applications to use barriers and schedule things the right way to allow us to overlap render passes. That gives us the best performance, and applications can throw away quite a lot of performance by not achieving that. Tessellation shading is a technique that is really designed for the immediate mode architecture. Read a simple model, do the tessellation, expand the geometry, but keep that expansion inside that FIFO, inside the GPU. It really doesn't fit for a tile-based architecture where we have to process things and write the tessellated data back out to memory. Similarly, geometry shading is bad. However, geometry shading is generally bad on all modern GPUs and shouldn't be used. So if you're looking at doing procedural geometry, please look at using compute shaders instead. Finally, tile-based rendering has this extra post-transform pass where we have to store the output of the vertex shader to memory. We have to read that back in. That implies both a bandwidth cost and a storage cost. And as we'll see a little bit later, some of these can have some strange side effects. If that's the hardware, this is a Vulkan conference, so what does Vulkan buy for mobile? One of the big pros of Vulkan is no driver magic. It was really a design constraint that goes into the design to try and remove some of the unpredictability that came from OpenGLES and OpenGL drivers, both in terms of performance hitching, but also in terms of memory hitching, memory footprint hitching. So Vulkan is one of those APIs that really gives you what you asked for, and this gives you predictable performance, and you can rely on the underlying behavior of the platform. Vulkan has a sensible threading model. It is designed for multi-threaded CPUs, so you can benefit from multi-core systems and have a much easier job multi-threading your renderer. It also has a much better threading model interfacing at the CPU and the GPU. OpenGL pretends that rendering is synchronous, so when you call draw, the API behaves as if the draw has already happened. That's not how the platform really works, so the driver has to try very hard to maintain that illusion. Vulkan just exposes that it's an asynchronous model, you queue up commands, the GPU processes them and comes back with results sometime later. Even though it's a bit more work on the application, it means the driver has to do far less state tracking to make sure things are rendered correctly. Similarly, Vulkan has a much more modern memory model, has the concept of persistent buffers and memory coherency, so we can have a much more lightweight approach to managing memory and exchanging data between the CPU and the GPU, especially on mobile where we have a unified memory pool, the CPU and the GPU sharing the same DRAM. And it has a much more sensible state model. OpenGL requires us to consistently and constantly rebuild states every draw call. Vulkan, we can pre-package those into pipeline objects and so on to only pay that cost once. I say mostly. The general feedback from developers is that we overcook the PSO. There's too much state in the program objects. With Vulkan 1.3 and dynamic rendering, that is getting a little bit lighter and a little bit easier. Just be aware of the fact that some of those dynamic states may come with a cost, even though it makes your life as an application developer a little bit easier. Ultimately, if you put all of these together, what you get, for the most part, is a platform with much lower CPU cost. The main benefit of Vulkan is more predictable memory, more predictable CPU, and on average, significantly reduced driver load. What Vulkan doesn't necessarily give you is faster GPU performance. We're exposing the same hardware with the same kind of functionality exposed through the API. So there's no real reason to expect Vulkan to be dramatically faster on the GPU, but you may get that, especially on mobile. If you're spending less power on the CPU, we can shift some of that thermal budget across to the renderer. The first downside of Vulkan is that there's no driver magic. OpenGLES drivers can hide some of the mistakes that application developers make and smooth out some of the hitching or the glitches by substituting sort of driver optimization. Because of how Vulkan is expressed at the API level, that's actually very difficult for a Vulkan driver to do. So some application developers notice a performance drop going from OpenGLES to Vulkan simply because the Vulkan driver is not helping them as much. So it's a pro, but it's also a con that you need to be aware of. Some of the lower driver CPU cost that Vulkan has is achieved because the driver is doing less. It's a thinner driver. We delegate more responsibility to the application. So some of the optimization in Vulkan comes from a driver needing to do less, but the application may need to do a little bit more instead. This is particularly around things like lifetime management and resource management, where OpenGLES would track all of that on a per resource basis. Vulkan simply says it's the application's job to do that. The good news is a well-written application can have a much more efficient implementation than an OpenGLES driver doing it. And the reason for that is that OpenGLES drivers have no knowledge about how those resources are going to be used. So it has to track every resource fully individually, and that can get pretty heavy. For an application implementation, you know the lifetime of your resources, you know the life cycle of your game levels and your load sequences. So you may not need to track each resource individually, you could track them as a set. For mobile in particular, we are aware of the developer feedback and the developer challenges looking at device fragmentation. And this could be API version fragmentation and the difficulty of using new Vulkan features, and it could be driver version fragmentation, bugs and issues in older drivers that don't get fixed. Just to acknowledge the issues, we do hear them, and we are trying to find solutions with our industry partners. So how does this translate into best practices? If we have a tile-based GPU using Vulkan, how do you get the best performance out of your application? And this really starts with efficient tile memory. We've ultimately pivoted our entire GPU architecture around the fact that we have this tile memory that keeps data on chip. If you make poor use of tile memory, you lose a lot of the advantages of being tile-based, but you're still paying the penalty of the geometry overhead. So this is really important to get right. For Vulkan, render passes basically define the tile memory lifecycle. So a load up defines how tile memory is initialized, and if you use a load up don't care or a load up clear, you won't load from memory, you'll just pre-initialize the tile to a clear color or an undefined value, and that's free in terms of bandwidth. The store up defines the finalize step at the end of the pass. How do you write the tile memory back, if you do at all? You store up don't care if it's transient and you don't need to keep it. Also back that by a lazy transient allocation. If you have read-only inputs, you can use store up none. It doesn't get stored, and it also doesn't invalidate the contents that are in memory, so you could read it again later. If you're using multi-sampling, then the resolve attachment is how you do the resolve on store. It's really important that you never store multi-sample data back to memory. For 1080p, with 4x multi-sampling, a store back to memory is going to cost you 32 megabytes, and the first thing you're going to need to do is resolve that manually, so you have to read that back in again, 64 megabytes per frame gone, just on a multi-sample resolve. Please never do it, just use resolve attachments. The good news is we don't see many developers getting that wrong, but it's always important to check. However, one thing that we do see is developers creating unnecessary render passes. So here we have an application at the top with two render passes, a 3D pass that's written back to memory, and then a UI pass which renders second. So it's going to read the image back in and just blend the UI layer over the top. So it's being read as a texture, and it's only ever being read on a one-to-one coordinate basis. There's no need to split this into two render passes. This could quite simply be a single render pass that's passed through the game engine, and the UI appends over the top. So the only reason to force a render pass is if you need an image that you're going to sample at a different coordinate, not one-to-one, or you need an image you can hand off to the swap chain, for example. So we quite often see game engines that are architected to pass around images, and that forces these splits between game engine subsystems. Where you can pass around render passes, just keep appending to them, and only flush the render pass when you actually need to read it as a texture, other than a one-to-one read. I do want to talk a little bit about Framebuffer compression. So AFBC is our lossless compression. It's been around for a while now. Because it's lossless, it's variable bitrate, so it may save you bandwidth, but it's can't save you storage. We have to allocate memory for the worst case, but it typically gives you around about a 2:1 compression ratio for game-like images. It could be a lot better for simple content like block color UI, but for game-like images, 2:1 is a reasonable rule of thumb. It's not supported everywhere. You can only read it on the texture path and write it on the Framebuffer write path. And to allow AFBC to be used, your API usage must conform to these constraints. This year, we'd like to introduce AFRC, ARM fixed rate compression. This is a new visually lossless compression, much like display stream compression, and it is a lossy fixed bitrate, but you really can't see the loss. We support it for 8-bit UNorm and sRGB images, both 1, 2, 3, and 4 component, and it has the same API usage constraints as AFBC. To use AFRC, you can opt in via the new VKX image compression control extension, and this allows an application to choose a compression ratio. And for AFRC, there's choices from 3:2 all the way down to 4:1. This potentially comes with some benefits over AFBC. It does depend a little bit on your content. So you have the potential for a higher compression ratio for your game-like images. You could get from typically 2:1 to 4:1. Because it's a lossy compression that's fixed bitrate, we can guarantee smaller memory footprint. We know we only have to store a quarter of the data if you choose a 4:1 compression. So your storage size in memory is smaller and your memory locality is better, so you may find that your performance improves slightly. The extension exposes a number of different bit rates per component, and there's some queries that will tell you for a particular vendor implementation what's supported. This is what we're going to expose for the first implementation of AFRC on the Immortalis G715. And as you can see, it does depend a little bit on which format you're using, but you can generally get from 3:2 down to 4:1. The obvious question is, what does this look like? So this is a G-buffer from the Manhattan benchmark from Khashoggi, and it's storing a 32-bit per pixel RGBA attachment, albedo in RGB, and there's a material mask stored in alpha. I've stripped off the alpha mask just for ease of presentation here. And so this is the uncompressed data. So this is the AFRC image using the highest compression ratio, 4:1 compression. This will give you typically a 2x bandwidth saving, going from 2:1 with AFBC down to 4:1 with AFRC, but it's going to give you also the 4x reduction in storage size. And if we say visually lossless, if I toggle back and forth between these two, it really is very, very hard to visually spot differences. AFRC is very effective at preserving hard edges and gradients in a way that means that you don't really notice the changes. There are differences here. If you diff the two images in ImageMagick, then you can see that they aren't the same image, I do promise. But even on a monitor looking very closely, it is very, very hard to spot the differences. So we're very excited to see what developers can do with AFRC going forward. It's not always the right compression to use. If you've got very simple images like material masks that are close to block color, AFBC is probably going to give you the best compression ratio. If you've got material data that can't cope with loss because you're using it as, say, an integer lookup index, and you don't want to corrupt the material ID that you're looking at, then this probably isn't the format for you. It's lossy. But for color data, this does look very compelling, and for a lot of content, frame buffers that are being written and read by the game are one of the largest contributors to the bandwidth the game produces. So this is potentially a way that you could reduce your game bandwidth by tens of %. On the fragment side, the final piece really is efficient swap chains. And as I mentioned earlier, this is really about making sure that you feed the DPU in a way that the DPU can handle the workload natively without that GPU fallback. So the display processor is outside of the GPU, and it handles composition tasks. And it may handle rotation, scaling, color conversion, layer composition at various resolutions, or it may not. And unfortunately, with the Query API in the Vulkan window system integration, you've got no way of telling. There is a Query API where you can query what the display subsystem can handle, but because that GPU fallback is available, everything can be handled, just not everything is necessarily efficient. So on Android, that query isn't useful for telling you what the DPU itself can handle. So the only thing you can assume is that the DPU is very simple and it cannot handle rotation. When you get the current transform hint for your surface coming back through the swap chain, recreate your swap chain if it changes, set your swap chain pre-transform to match the surface current transform, and apply any rotation you need as an application side geometry transform. This tells the window system that everything's in the correct orientation, and the DPU can just scan out the image straight away. The second part of this is looking at scheduling, and this is really coping with the fact that by going tile-based, we have to split the rendering pipeline into two disjoint pieces. So this is the kind of scheduling that we want. We have the application building a render pass, submitting it to the geometry pipeline. That has to run to completion before we can start any fragment processing. And to keep the hardware busy and to keep the CPU busy, we want to pipeline these so that we keep all of those stages running. So while the fragment processing for an earlier pass is running, the geometry processing is running for the next pass, and the application software is busy building the render pass for the next pass. Firstly, from an application point of view, please don't hold on to your render pass submits until the end of the frame. Try and submit your major render passes as you go through. If the geometry pipeline happens to be idle, that just gets that workload started as soon as possible. The next thing is making sure that when you're expressing pipeline barriers in your command streams, that you do so in a way that allows us to overlap the vertex and fragment processing stages. Generally, the most common use case is a fragment shader rendering to a texture that is read by a later fragment stage. To achieve that with pipeline barriers, set source stage to all graphics, set dust stage to fragment. This allows all the stages prior to fragment to run before the earlier work is completed. So here in yellow, you can see the F0 vertex work is running while the green F0 fragment work is still running. In terms of behavior, you can see the fragment pipeline, which is our most heavily loaded in this diagram, is staying busy all the time. Vertex shading is going idle because there's not quite as much vertex work to do. But the busy pipeline stays fully utilized. This is going to give you the best overall performance and energy efficiency. So the general rule of thumb here is make sure your source stage is as early in the pipeline as possible, and make sure that your dust stage is as late in the pipeline as possible. That gives us the best chance of achieving overlap. The bad case is pipeline barriers that serialize the world, and the most common case we see, especially copied from some of the early tutorials, is source stage is bottom of pipe, dust stage is top of pipe. This removes any chance we have of doing overlap. The top of pipe of one submit has to wait for bottom of pipe of the previous one, and so even though the vertex work may not need the output, we don't know that and it can't start. As you can see, we're going to run things serially and the overall performance will take a significant hit. So for tilers in particular, this is one of the most important things to get right. If you don't do this, you're going to throw away an awful lot of performance. A slight aside, just in terms of tooling, we see quite a lot of developers coming from PC and console trying to use timer queries as a profiling tool on a tiler. And just be aware of the fact they can be very misleading. If you try and time render passes, putting a timer query at the beginning and in the end, and then measuring the elapsed time, the first thing you'll note is that there's some time here where your render pass isn't running at all. So in the middle there's no blue box. The blue fragment shading is just waiting for the fragment queue to free up. But from the point of view of the timer query, it doesn't know that, and so the elapsed time can include periods where your render pass is not even running, and it's also going to be influenced by other render pass work from the application that's running in parallel. So you're not necessarily measuring the workload that you think you are. This could be a use case where deliberately introducing serialization is a good idea. So you could do bottom of pipe, top of pipe dependencies just in debug builds, and then put in timer queries. That probably would give you something that you could measure. Your overall frame wall clock time is no longer representative because you've lost the overlap, but the individual render pass timing should be stable, and as you apply optimizations, you can see whether that timing goes up or down. Most importantly for a tiler, never try and use timer queries to time draw calls, because draw calls don't exist as a nice kind of monolithic piece of work that you can time. There'll be a bit of work in the vertex shading stage that's usually nicely contiguous, but your fragment shading is going to be tile by tile, and which tiles get shaded for a draw call just depends where the triangles are on the screen. And they're not necessarily a nice block, and they're going to be scattered with other draw calls finally interleaved. So there's nothing a timer query can do to return sensible timing for a draw call. All we can say is the draw call started at the start of the render pass, and it finished at the end of the render pass, and the elapsed time is the whole render pass. So timer queries for draw calls simply make no sense on a tiler. This then moves on to the geometry side of things. We've talked a lot about scheduling and the fragment side. We know geometry is one of the weak points of tile-based rendering. We have some extra traffic that we have to process. And the first thing I'd like to do is make an appeal to the artists out there. This is the size of a typical mobile texel, right? And usually for art assets coming into your application on mobile, that's going to be ETC2 or ASTC compressed at around about 4 bits per pixel. This is the size of a typical mobile vertex. It's about 32 bytes. It's not the best mobile vertex. A good mobile vertex using good packing and good data type selection is maybe 20 bytes. But I've seen mobile content with 40, 48 bytes as well. So 32 bytes is kind of typical, but personally I'd like it a little bit smaller. The first thing you'll note is that 32 bytes is a lot bigger than 4 bits. So texturing is an area where the industry has put a huge amount of effort into optimizing. Especially with ASTC, you can really squeeze the bandwidth right down if your images allow it. So in terms of being efficient with bandwidth, try and model things with textures rather than modeling things with detailed geometry. Have just enough vertices to maintain the silhouette integrity of your render, right? The silhouette's the one thing you can't fake in shaders. And then use textures to apply everything else. Fine detail for diffuse, normal maps for correcting lighting, and so on. Right? You can do a lot of things with textures at 4 bits per pixel that would be much more expensive to model with vertices. And the reality is it's far worse than this when it comes to geometry. Your effective vertex size may be double what you think, and this is nothing to do with us being tile-based. This is purely because for every front-facing vertex that you keep, there is likely a back-facing vertex on the back of your model that was culled, but it still gets loaded, it still gets vertex shaded, because we need to know where it is on screen before we can cull it. So your effective vertex size is significantly larger, again, swings in favor of texels, and then on top of that you have some penalty from tile-based renderers storing some per vertex data somewhere as part of that handover between vertex and fragment shading. Exactly how much depends on the hardware generation and depends on how much data your vertex shader is writing, but it may almost double the bandwidth again. So just be a little bit wary of triangles and vertices. They're very expensive. Try and optimize them very aggressively in terms of size in memory, and really use them very sparingly. Try and use them to model the silhouette shape of the object, but for everything where it's internal detail, please simplify the geometry, try and just use textures as much as you can. One thing you can do to make the geometry processing more efficient is to make sure that your memory layout of your attribute streams plays nicely with tile-based hardware. So most vendors, this isn't just Mali, will do some kind of position shading first to compute where the triangles are on screen, put that through clipping, culling and binning, and then only for the visible vertices run the varying shading, the rest of the vertex shader for the things that aren't position. And then that data gets written back to memory. The traditional way of passing in input data is to use fully interleaved vertices. So just have a single array of structures. In this case, we have a position, tangent, normal, and texture coordinate just interleaved. The downside of this approach is that when you run the position shader and you fetch position, DRAM is optimized for fetching large bursts. So we're going to fetch a 64-byte line out of DRAM, and that line is going to contain position, tangent, normal, and texture coordinate, even though we don't need most of those for position shading. We only need position. So for the vertices that we throw away, we're fetching a whole load of data that we don't really need. And even for well-written applications, remember that you're always going to throw away around about half of your vertices. They're in the frustum, they're inside the camera shot, they're just back-facing, so you can't see them. And that's vertex load the application can't cull efficiently. The best thing you can do for tile-based rendering is to use split streams, put a interleave stream of all of your position inputs, then have a second interleave stream of everything else. This means that when that position shader runs, you just load positions, you don't pollute the cache with data you don't need, you don't fetch data you don't need from DRAM, then we only fetch the others for the vertices that survive clipping and culling. As you can tell from the image, we use this technique with King for their Crash on the Run game. There's a whole talk at it from GDC 2021, and using this technique, they achieved a 15 to 20% reduction in their game bandwidth. The nice thing for this technique is that it doesn't change the look of your content on screen at all. Right, this is the same geometry, same triangle density, we're just changing how we upload the memory layout. It's art neutral, and it's going to give you a significant saving. We do need to talk about device lost errors, and there are a few Marley-isms that we've seen developers trip over in the last couple of years that we just wanted to highlight. So if you hit a device lost error and you think it might be one of these issues, you have somewhere to get started. The ARM GPUs today shade vertices in groups of 4 contiguous indices. We can shade indices that your index buffer skipped. So here we have an index buffer with 3 indices in. We're going to end up shading 12 vertices, including many that your index buffer didn't contain. First of all, this can cause some overshading cost in terms of vertex shader invocations. So first advice is tightly pack your index ranges. Find the min index and the max index and make sure that you use all of the indices in between. Don't sparsely sample. We commonly see that if people are generating mesh level of detail by using sparse sampling. Please don't. Just create a dedicated tightly packed vertex range for each LOD level. The one that catches people out is that we can often shade indices that your index buffer didn't even contain. So here we have an array of 9 indices, 0 to 8. Again, because of the grouping of 4s, we're going to shade 9, 10, and 11, even though they may not exist. And that can run off the end of your mesh data in your buffers. If it's a direct attribute access, we guarantee it won't run across the end of the buffer bounds, but it may cause a fault on indirect load if you're using that value to address another array in the shader. Recommendation here is if you are using any indirect loads in your shaders, pad your meshes to a multiple of 4 vertices. Just replicate the last vertex as many times as needed to do that. That guarantees that the out-of-index shading won't cause any problems. The other one is just be aware of intermediate storage. We have data coming out of the vertex shader that Marley needs to store somewhere, and for Vulkan drivers we typically have a backing store of 180 megabytes per render pass, and if we fail to allocate memory into that 180 megabyte pool, then you'll get a device lost error. So the most simple fix here is to minimize geometry complexity. However, it's not normally the geometry complexity itself that causes a problem. On the older GPUs, the Midgard family and the Bifrost family, the implementation scans the index buffer to find the min index and the max index, and then allocates memory for that whole range. Even if there's big gaps that you don't reference in the index buffer, we allocate memory for all of it and then sparsely use it. So the main reason we see out of memory areas is sparse indexing, where the application just forces the driver to allocate a huge range that isn't really needed. Again, tightly pack your index ranges to reduce the min-max span, so we don't over-allocate memory. Be a little bit wary of the console technique, where you have a large index, like a uint32 index, and you pack metadata into the high bits. That can bloat the min-max range. If you want to use metadata, you can, but we recommend you just have a separate uint array in memory that you index from the vertex shader. For the Valhalla GPUs, it's much better. We only allocate memory for visible vertices. There's no scanning for min and max. And the command stream GPUs, Mali G710 onwards, use a more flexible allocator that can exceed 180 megabytes per render pass. But again, recommended that you tightly pack index ranges to minimize overshading. To wrap up, I just want to talk very quickly about what's new in the devices that you'll be targeting on the market this year. Last year's new devices are now becoming more mainstream. So this is the Mali G710 family, which includes the Mali G610, the G510. So these are Valhalla architecture GPUs with our command stream front end. So it's a 4 pixel per clock shader core chassis. So it's twice as big per core as the earlier generation. And the biggest change is that we now have native command stream support in the GPUs. So we can, all of the Vulkan command stream operations are more or less processed directly by the GPU itself with minimal CPU driver involvement. This significantly lowers the CPU overhead of the drivers, both for scheduling and command stream enqueue, which is good for CPU power. It also gives us native support for stream operations that require some processing. Indirect draws, secondary command buffers. So for indirect, we also support indirect draw counts, so you can do multi-draw indirect. And we also have native QSync for lower overhead Q interop. So this overall removes a few of the historical best practice disk recommendations, because we can now handle those effectively with the command stream processor, and also generally gives you more CPU headroom for the application, or thermal headroom that you can reassign to graphics. We also get the lossless framebuffer compression, AFBC, for EP16 formats, including RGB and RGBA. That can significantly reduce bandwidth for HDR rendering. We also get faster scheduling for tile memory access if you're trying subpass merging, or pixel local storage, or framebuffer fetch. The latest headline GPUs are the Immortalis G715 family, but there's also the smaller Mali G715, Mali G615. The headline features for this are ray tracing and variable rate shading. There are some other talks in the Vulkanised video on YouTube from my colleagues Jose Emilio and Albin. We also have conservative rasterization and the ARM fixed rate compression that I explained earlier. So those are all new features that an application can opt in to use, and there's some pretty big ones there. Ray tracing and variable rate shading are big new technologies that enable a whole pile of new use cases that we're very excited to see what developers do. But on the shader core side, there's also a huge number of improvements that are just a bigger, faster, more capable core that will help a lot of existing content or more mainstream shader content that's out there. So we have a faster shader core that can do twice as many FMAs per clock, 4 times faster subgroup operations, and twice as many varying interpolations. For texturing, we've improved the performance of cube mapping and texture LOD, so that's twice as fast. And we've also improved a number of common memory access patterns that we see in shaders. So load store access for common uniform loads that haven't been promoted to uniform registers, and stack access should now be much faster. In addition, to complement the FP16 compression in G710, we've also added hardware blending and multi-sample resolve for FP16 formats. If you'd like to find out more information about Mali or developing on Mali, or you have questions, please sign up for our developer program. You can also find us on Discord, Twitter and YouTube, and we always welcome questions on our community forums. For our documentation and best practice guides, please check out developer.arm.com/graphics. Thank you very much.